In this lecture, we're going to look at the three types of acids and bases that exist in a reaction: Arrhenius acids and bases, Lewis acids and bases, and Bronsted-Lowry acids and bases. Now, Arrhenius acids are those compounds that produce hydride ions in water, or they increase the concentration of H+ ions found in water. So, for example, let's look at HCl. HCl dissociates in water into an H+ ion and a chloride ion. And that means because HCl increases the concentration of our H+ ions found in water, by definition, HCl must be an Arrhenius acid. Now, Arrhenius bases are those substances that increase OH concentration in water. So, for example, let's look at sodium hydroxide. Sodium hydroxide, when mixed with water, dissociates into sodium and an OH ion. And that means it increases the concentration of our OH ions found in water. Therefore, this guy, by definition, must be an Arrhenius base. Now, Arrhenius acids and bases are always found in water. That's by definition. Whenever we talk about Arrhenius acids and bases, we talk about solutions in which our solvent is water. So let's look at this reaction again. So we know that HCl, when mixed in water, dissociates into a hydride ion and a chloride ion. So now we have a solution that contains a bunch of H+ ions floating around next to water. So what actually happens is a base pair, or a pair of electrons found on the water, grabs the H ion, producing hydronium ion. So actually, the hydride ion produced by an Arrhenius acid is always associated with a hydronium molecule. And that's because our solvent is always water. According to the Arrhenius acid-base concept, in aqueous solutions, the hydronium ions are responsible for acidic properties, and the OH ions are responsible for the basic properties. Now, one problem with such a definition exists. Molecules, such as ammonia molecules, that produce basic solutions and react with acids, and yet they have no OH ions. So if we look at the structure of NH3 ammonium, we see that it contains 3 H's, 1 N, and a pair of electrons. Clearly, it has no OH ion, so according to our Arrhenius acid-base definition, this cannot be a base. Yet, it has basic properties. So, this definition isn't that good. So they came up with a better definition, a definition that includes many more bases and many more acids. And this concept is called the Bronsted-Lowry acid-base concept. So, Bronsted-Lowry bases are those molecules that can accept a hydride ion using a lone pair of electrons. So let's look at the reaction of ammonia and water. So in ammonia, we have an extra pair of electrons. And in fact, this pair of electrons will take away an H ion from the water molecule. And this will produce ammonium and hydroxide. So by definition, because this guy has an extra pair of electrons, a lone pair of electrons, it acts as a Bronsted-Lowry base. Now, a Bronsted-Lowry acid are those molecules that can donate a hydride ion. So for example, let's look at the reaction of nitric acid and water. So nitric acid has an extra ion, extra hydride ion. And in fact, the water has an extra pair of electrons that will take away this ion. And this will produce hydronium ion and this ion here. That's negatively charged. So, by definition, nitric acid, because it could donate an H, it has an extra H, it acts as a Bronsted-Lowry acid. Now notice something interesting. In this reaction, our water acted as an acid, a Bronsted-Lowry acid, because it donated an H, right? It gave an H to this guy, producing ammonium, and became hydroxide itself. So it was a base here. I'm sorry, an acid here. In this reaction, it took away an H. And because it took away an H, it was acting as a base. It accepted an H. So in this case, it was a base In this case, it was an acid. One interesting thing about a water molecule is that under basic conditions, it acts as an acid, and under acidic conditions, it acts as a base. Our third and final definition of an acid and a base is the most basic definition, and this concept is called the Lewis acid-base concept. Now, this includes all the Bronsted-Lowry acids and bases, and many, many more. So let's look at a Lewis acid. A Lewis acid is anything that accepts a lone pair of electrons to form a new bond. And this bond is usually called a coordinate covalent bond, and we'll see why in a second. So we have BF3 plus an H that has a lone pair of electrons forms a coordinate covalent bond, HBF3. And it's called coordinate covalent and not covalent because both electrons come from a single atom. Remember, in a covalent bond, one electron comes from here and one electron comes from here. But in this case, both electrons come from a single atom. So let's look at the structural depiction of BF3. BF3 has 3 H's attached to the boron, and the boron has an empty orbital. And this empty orbital is what interacts with the lone pair of electrons on our H, forming our coordinate covalent bond. So, in this case, the BF3 accepted the pair of electrons because it had that empty orbital. So the BF3 is our Lewis acid. So another way to talk about a Lewis acid is to say that a Lewis acid is either neutral or a cation, in this case it was neutral, that has an empty orbital. Now let's look at Lewis bases. A Lewis base is anything that can donate a pair of electrons to form a new bond, a coordinate covalent bond. Let's look at one of the most basic reactions. An H atom plus a water molecule gives you a hydronium ion. So this is a cation that has an empty orbital. So this must be a Lewis acid. Remember, a cation and an empty orbital. Plus water. Well, water has what? It has a pair of electrons. It means it can donate a pair of electrons. So water must be our Lewis base. And these guys interact to form hydronium ion. So in this case, in this reaction, this was our Lewis acid, and this was our Lewis base. So once again, whenever we talk about Lewis acids and bases, we talk about a transfer of electrons. Whenever we talk about Bronsted-Lowry acids and bases, we talk about a transfer of hydride ions.